Hello everyone, welcome to my YouTube channel. This is Enoch's Tutorials. Don't forget to like and subscribe after watching the video so you can receive every update from this channel. In today's lesson, we are going to look at amines. That is an organic compound which is basically studied in organic chemistry containing a nitrogen atom. We are going to look at the nomenclature of amines, the classification of amines, and the type of reactions that amines undergo. Don't forget to like, subscribe, and also share to whom it may concern after watching, so you can receive every bit of update from this channel. So let's begin. So what are amines? Amines are basically organic derivatives of ammonia. So this is an ammonia. When nitrogens around the ammonia, or let's say around the nitrogen atom in ammonia, is replaced by an alkyl group, a cycloalkyl group, or an aromatic ring or an aromatic group, that compound qualifies to be called an amine. So when a nitrogen in the ammonia, or let's say the hydrogens around the nitrogen ammonia, is replaced by an alkyl group like methyl, let's say ethyl being its propyl, or let's say an aromatic group like phenyl group, or let's say a cyclohexyl group, which is a cycloalkyl group, that compound qualifies to be called an amine. So that's what an amines are. Three examples are what we call a methylamine, in which one nitrogen or one hydrogen of ammonia is replaced by methyl. You can have trimethylamine, in which all the three nitrogens have been replaced by three methyl groups. You can have methylpropylamine, in which one hydrogen has been replaced by methyl, the other has been replaced by methyl to form this compound. The next we can talk of is methylphenylamine. And methylphenylamine is when one nitrogen is replaced by one hydrogen is replaced by a phenyl group or benzene ring. The other is replaced by a methyl. They can have cyclohexyl dimethylamine. So here the two hydrogens has been replaced by methyl groups, and the remaining hydrogen has been replaced by a cyclohexyl group. So when any hydrogen in ammonia is replaced by any of these three groups, that compound qualifies to be called what we call an amine. So let's see the various classifications of amines. So amines can be classified based on the number of carbons bonded to nitrogen. So you can have an amine with only one carbon bonded to it, which we call the primary amine, the one with two, which we call the secondary amine, and the one with three, which we call the tertiary amine. So you have three main categories of amines. You can have primary, secondary, and tertiary. So these are the classifications. You can have an ammonia, the one without any carbon. You can have methylamine, the one with one carbon, which is a primary amine. Then the one with two carbon, which here we call the dimethylamine, which is a secondary amine, and a tertiary amine where all the hydrogens has been replaced by a methyl group. So here the nitrogen here is bonded to three different carbons. So if the nitrogen is bonded to three carbons, we call it tertiary. If it's two carbon, it is secondary. If it is three, or if it is one, it is primary. And if it is none, it is called ammonia. Let's continue with the nomenclature of amines. How are amines named in organic chemistry? So common and IUPAC names of amines are used for naming amines. In the common systems, the rules are just similar to what is normally applied in some organic compounds like ethers, like naming of alkyl and aromatic groups, first to the compound and then followed by amine. So the common way of naming amines is by naming the alkyl or the aromatic groups bonded to the nitrogen, then followed by the amine. So here you can have the alkyl group bonded here is methyl. So the common name of this compound is called methylamine. You can have here trimethylamine and also methylpropylamine. So with the common way of name or the common nomenclature system, you just name the groups bonded to the nitrogen, that is the alkyl and aromatic groups. then you follow it by amine. That's how the common nomenclature of amines are done. Now, per the IUPAC nomenclature, the rule is just simple or similar to what is normally applied in all organic compounds, being it alkanes, alkynes, alcohols, aldehydes, ketones, carboxylic acids, or even esters. The rule still holds for the same or for naming amines too. Let's see the rules for naming amines, the IUPAC nomenclature system. So in naming amines with the IUPAC nomenclature system, you just have to select the longest carbon chain which has the nitrogen, take that as a parent chain, then name the parent chain by changing the corresponding alkane name for this chain by dropping the E and adding amine. So if the parent chain is, let's say, having 3 carbons, its alkane is called propane. So to name it as an amine, we call it propanamine. That is, the last E is dropped and followed by amine, which is an amine. Then here you number the chain to give the nitrogen the lowest number. Then the number and the identity of the other substituent, including anyone on the main chain, are indicated at the beginning of the amine. So let's take examples like this. So here, if it was to be a common nomenclature system, we can say, let's say, we can make it sec-butyl amine. That's the common way. But here, if we are to apply the IUPAC nomenclature system, the position of the amino group is indicated with the 2. So here, this is the parent chain. You start numbering from here. Here's 1, here's 2, this is 3, and this is 4. So the 2-butan amine here, if it is alkane, it is renamed butane. So it becomes butan amine, but it is 2-butan amine because the amino group, which indicates the functional group of amines, is at the second position and is the longest chain. Let's take this one too. You start naming from here: 1, 2, 3, 4, and the amino group is at the first position because we want to give the least number to the nitrogen, so it becomes 1-butan amine. Take note, in naming amines, not like the other compounds, we don't start numbering the nitrogen. We only number the carbons. So in naming amines, we don't include the functional group as the first number. No, unlike the other compounds. We can have this one where NH2 substituted alcohols or other compound cases are involved. The amino group is called an amino substituent. So we can have cases whereby we have other compounds which are also other functional groups which are of higher priority than the amino group. In such cases, the functional group is named as a substituent. For here we have a carboxylic acid functional group and amino group, but carboxylic acids are of more priority than amino groups. So here we name the amino group as a substituent and the carboxylic acid as the parent organic compound. So this compound is going to be named 3-amino-butanoic acid. 3-amino-butanoic acid. Let's take this one too. We can have 4-amino 4-chloropentanone. So this one is a pentanone, which is a ketone, which is regarded to have, let's say, higher priority than amino group. So here it is named 4-chloro because we have chlorine here. Start number from 1, 2, 3, 4, and 5. So it becomes 4-chloro, or say 4-amino 4-chloropentanone, 2-pentanone. Here it is amino first because here the A comes before the C. The names are done in alphabetical order. So let's see some functional group priorities which may occur in organic compounds. If this set of functional groups occur in the organic compounds, now this is their suffixes and this is their prefixes. So for, let's say, carboxylic acids, their suffix are oic acid, so ethanoic acid. You can have ethanoate, you can have ethanamide as all this. You can have aldehydes too. If aldehydes occurs in an organic compound, the oxo is how it is named, or its prefix is called oxo and its suffix is called al. So aldehyde is also called alkanals. Ketones are also called alkanones. We can have alcohols. you can have amines, and the rest. So this is the priority, how they are arranged in order of priority if they occur in organic compounds. So if they occur in organic compounds, the aldehydes are regarded to be of higher priority than all. So in all organic compounds, carboxylic acids have the most priority, followed by esters, amides, aldehydes, ketones, alcohols, amines, alkenes, alkynes, alkyl ethers, ecarbenzene, and alkenes. So if any of these compounds or any of these functional groups occur, two or more of these occur in the same compound, the one which is of high priority is regarded to be that organic compound, and the one of lower priority is named as a substituent. Take note of that. Aromatic amines involving an amine type nitrogen bound to an aromatic ring. The simplest case for this is an aniline. So aniline is an aromatic amine. Aniline is an aromatic amine. How do we name it? If the benzene ring has substituent around it, we start numbering the carbon from the carbon with nitrogen. So here this carbon 1, this carbon 1, here this carbon 1, this is carbon 2, and this is carbon 3. So to name this compound, the parent compound here is aniline. So its name becomes 3-bromo 2-chloroaniline. It is bromo because B comes before C in alphabetical order. In cases whereby the substituents are bonded to the nitrogen, we indicate the position of the substituent with N and not numbers in this case. So here, if if the substituents are on the nitrogen, you indicate the position of the substituent with N to show that it is on the nitrogen and not the ring. So here, this then becomes N-ethyl, N-methyl aniline, N-ethyl, N-methyl aniline. Here, this ethyl is on the N and this methyl is on the N, so it becomes N-ethyl, N-methyl aniline. In the same way too, with this one, the methyl is at position 3, then and the methyl is at position N, so the name becomes 3N dimethyl aniline, 3N dimethyl alanine. Take note of that in naming amines. Okay, so let's look at some physical properties of amines. So some physical properties of amines. So amines tends to be gases for low molecular weight amines. That is, amines of let's say 4 or less number of carbons exist in gases at room temperatures, whereas those that have a higher molecular weight exist as liquids. All amines exhibit strong odors as shown here, and they also have what you call a fishy smell. A fishy smell. A common amine is the putrescine and also cadaverine. These ones have a very strong odor and they have a fishy smell. Other properties of amines include their boiling point comparisons. So amines boiling points are intermediate of those of alcohols and alkenes of similar molecular weight. Now let's see the chemistry behind why amines of similar molecular weight between alcohols and alkenes tend to be intermediate between the two. Now amines have nitrogen, and because of the presence of the nitrogen in amines, in primary and secondary amines, there is a possible hydrogen bonding system which can exist in amines. Now, the nitrogen is not as strongly electronegative as compared to oxygen. Therefore, the hydrogen bonding in alcohol is going to be stronger than that of amines. Hence, alcohols will have a very strong molecular weight, or let's say higher boiling point as compared to amine, because alcohols can form a very strong hydrogen bonds than amine. Unlike alkanes or any of the hydrocarbons that have no possible hydrogen bonds, amines will have a very higher boiling point than the corresponding alkanes, but will have a very lower boiling point than alcohols because of the highly electronegative oxygen which makes them form a very strong hydrogen bonds in alcohols than in amines. Amines may tend to be water soluble because of the hydrogen bond which can interact with water. So amines that have a fewer carbons of 6 are indefinitely water soluble, but those which may have a higher boiling point or higher um, number of carbon that is beyond 6 may be water insoluble. So the water solubility of amine may decrease when the chain length increase and when the degree of nitrogen substitution increases. So if all nitrogens are substituted, it becomes less soluble because there's no exposed hydrogen to form hydrogen bond then which can initiate solubility. So tertiary amines will be less water soluble as compared to secondary amines, as also compared to primary amines if they all have, let's say, a comparative molecular weight. Now let's go through some chemical reactions of amines. So the kind of reactions that amines can undergo in organic chemistry. So amines are similar to ammonia in their reaction because they all have nitrogens. Amines are basic because they have some kind of lone pairs around them, which also make them nucleophilic, and they react with alkyl halides, is acid chlorides, and carbonyl compounds. So amines can be basic and also nucleophilic because of the lone pairs of electrons. They are basic because they can accept protons to form a cation, and also nucleophilic because they have lone pairs of electrons to attack a positively charged or a positively highly electropositive compounds. The aromatic amines are highly reactive in electrophilic aromatic substitution reactions. So we are going to look at them in the next few slides to come. So these are the given reactions of amines which we are going to discuss in this video. We're going to look at the reactions of amines as bases, the reactions they undergo as an alkylation reaction, how amines are converted to amides, Hofmann's elimination from quaternary ammonium salt, reactions with nitrous acid, carbyl-amine reactions, how amines are oxidized, and substitution reactions in benzene amines like aniline. So here, the reactions of amines are very simple. Amines have lone pairs on them, so they can easily abstract a hydrogen from an acid to exist as an anilinium chloride, or say an aminium ion. So here, the amine can take this one to assume a positive charge, leaving the chlorine in the solution. So because of this tendency, aniline in this case act as a base because it can abstract a proton from this one. What is then is a base? A base is any entity that can abstract a proton or that can donate an electron to a species. So here the nitrogen here can abstract a proton or can donate a proton to the space. So here both two scenarios define what we call a base. In the previous video, we discussed acid and bases, and we discussed how acids and bases are defined by some scientists like Lewis acid, like Bronsted-Lowry, and Arrhenius' definition of acids. Just check up on the channel and look at how we define this. Realize that bases can be defined as proton acceptors or electron donors. In this reaction, we also see that the ethanoic acid here acts an acid and can donate this proton to form an ethanoate, and this proton can be accepted by this compound. So here this amine acts as a base. Let's look at some alkylation reaction. As we said, amines are basically nucleophilic, so alkyl groups can be added to amines to increase their alkyl share or the alkyl portion of it. So let's look at this reaction. This is a primary amine which can be alkylated to form a secondary amine, which can further undergo alkylation to form a tertiary amine, which can also undergo further alkylation to form a quaternary ammonium salt. So amines react as nucleophile with alkyl halides via substitution reaction. So here, one of the hydrogens is replaced by the alkyl portion of the alkyl halide. This reaction is called a substitution reaction. Tertiary amines, because they have no extra hydrogens, they react to form what we call a quaternary ammonium salt in this case. So this one is a tertiary amine which react with this one to assume a plus charge, which we call a quaternary ammonium salt. Typical reactions of alkylation reactions of amine are this. So this one is 1, 2, 3, 4. So butyl bromide plus ammonia forms an amine. Propylamine plus this ethyl halide can also form N or methyl N-propylamine. So here we can see that this ethyl portion replaces one of the hydrogens to form a secondary amine. Similar to this reaction, when aniline reacts with 2 moles of ethyl, all the 2 hydrogens will be replaced by the ethyl. In the same way, if you have excess of, let's say, methyl iodide, you can have a butyl trimethyl ammonium iodide. That is, there's going to be a sequential and repeated reaction in this case. Let's look at how amines can be converted to amides. So in amide reaction, amines can react with acyl chloride to form an amide. So when amine reacts with an acyl chloride, the chlorine will be replaced by the air, where this chlorine will abstract one of the hydrogens from the amine to form an HCl, and these two will interact to form what we call an amide. A typical open reaction, this is the structure of amide. So this is an amide, the functional group. The amido group of amide is this. This portion comes from the acyl chloride, and this portion, sorry, it's a ketone, I think I'm mistaken here. This is the amido group. The amido group of, let me change it so that I can see it clear. Okay, this is the amido group of an amide. This portion comes from the amine, and the whole of this comes from the acyl chloride. So primary amines can react with acyl chloride to form an amide. Secondary can react to form an amide, but tertiary does not form an amide because it has no nitrogen for replacement or substitution. Another known reaction of amine is what we call Hofmann's elimination from quaternary hydroxide. Quaternary hydroxide is an amine, or let's say an ammonium ion, when nitrogen has, let's say, 4 or even more of ethyl portion. So this is a typical quaternary hydroxide. It's a quaternary hydroxide. If you react this amine with excess of this, you're going to produce a quaternary hydroxide. So this reaction or this compound upon oxidation with silver oxide can produce an alkene and a tertiary amines. So the reaction, the first is the exhaustion methylation reaction with an ethyl halide, oxidation with silver oxide, then a heat to eliminate alkene. Let's look at how amines are generated from Hofmann's elimination reaction. First, the amine is reacted with excess of the ethyl halide to form the quaternary hydroxide. Next, the quaternary hydroxide is oxidized with silver oxide to produce a hydroxide ion and silver iodide. So the silver portion of this will replace or react with the iodine or the halogen from the ethyl halide to produce a silver halide. Then upon heating, there is going to be elimination of this portion to form an alkene and a tertiary amines. This reaction is very similar, and also is also called the Cope synthesis of tertiary amine. Cope synthesis, the same mechanism, it works for the same mechanism. So here, this plus secondary amines undergo this. These are typical examples of Hofmann's reaction, Hofmann's elimination reaction. In cases whereby the quaternary ammonium or the quaternary hydroxide is on a secondary, as seen here, is on a secondary carbon, there can be possible formation of different alkenes. You can form the alkene here, double bond here or here. So in these cases, we are going to produce multiples of product. So the chief product is the one that is more stable. The next reaction of amine is what we call a carbonyl reaction. And this reaction is a test reaction which is used to test for the presence of primary amines only in a mixture of compounds. When primary amines are heated with a chloroform in alcoholic potassium hydroxide, it produces an isocyanide which gives an unpleasant smell. So primary amines can be tested with through a carbonyl reaction by heating it with alcoholic potassium hydroxide in the presence of chloroform, and that gives it an unpleasant smell because of the formation of the isocyanide, which is also called the carbylamine. So the isocyanide of the carbylamine gives the unpleasant smell of primary amines when heated with alcoholic potassium hydroxide in chloroform. This is a chemical test of amine. Aliphatic amines can form the isocyanide. Aromatic primary amines can also form the isocyanide, but secondary and tertiary amines does not undergo this reaction. So primary amines can be distinguished from secondary and tertiary amines through a carbylamine test. Amines can also be oxidized with potassium permanganate in the presence of sulfuric acid to alcohol to aldehydes, as in here. Ethylamine, when oxidized with potassium permanganate in sulfuric acid, it can yield ethanol in this sequential reaction. After yielding this intermediate, which is not stable, when reduced, can form the ethanol and remains of ammonia. When primary aliphatic amines are oxidized with potassium, aromatic amines are oxidized with hydrogen peroxide. It also gives a nitrobenzene and water molecule. So nitrobenzene can be produced by oxidation of, let's say, an aromatic amine with hydrogen peroxide. Amines can also undergo a substitution reaction if it's an aromatic compound. In this case, if an amine is bonded to an electron donating group like an amino group like this amino group tends to give electrons to the system, hence it will increase the electron density of the aromatic ring. Now this one, the amino group is an auto para director. So when reacted with, let's say, a halogen like bromine, it will occupy all the spaces of the auto para position to form a tri-substituted aniline. This reaction is very fast. So the two auto groups and para groups attack at the same time because the electron density of this benzene ring is highly nucleophile, is highly increased, and the bromine here is highly electrophilic. In this case, though aniline is an electron donating group and also an auto para director, but when treated with an acid like nitric acid, it directs to the meta position. The reason being that the NH group here first acts as a base and accept a proton to form an anilium ion. This anilium ion makes it a meta director. So there's going to be a produced intermediate. This one is a meta director which directs an incoming nitro group to a meta position. You may think that maybe the amino group should allow at the auto para position. No, but when treated with acid like nitrous acid or even sometimes with sulfuric acid or nitrous acid, it directs at the meta position as shown here. When reacted with sulfuric acid, which is more of a sulfonation reaction, it is very surprising that it allows it at the meta para position because it gives what we call a zwitter ion in an aqueous solution. Here, this zwitter ion still allows at the position of para. It is not an anilium ion as seen in nitration, but a zwitter ion, which is more of a para director, hence allows the sulfonation at the para position. So this is a very short video on amines. Thanks for watching. Don't forget to subscribe and like after watching, so YouTube can share this video to many people, and also you yourself share it to anyone it may concern. Thank you.